Okay. All right, so it's a great pleasure to have Fabio Apruzzi today from Padua, and he'll talk about Gaillard-Zumino and non-invertible symmetries. So thanks. Take it away.
Well, first of all, thank you for inviting me to speak at the Symmetry seminar. And I have to apologize because I'm coming out of a cold. So if I cough or I have to sneeze, don't worry. But I apologize in advance if I interrupt because of this. Okay. So today I'm going to talk about this paper that appeared in October in collaboration with Luca Martucci, which is about Gaillard-Zumino models and how to interpret some of the invariance of this model in terms of non-invertible symmetries. So before giving you the main aspects of the construction, let me just tell you what these Gaillard-Zumino models are and motivate a bit why they're interesting and where they appear. So Gaillard-Zumino models are effective field theories in four space-time dimensions, and they have a Lagrangian, which depends on gauge field. So the field content is given by n gauge field, and it depends on some neutral sector. So neutral means that they are not charged under the gauge fields, and this can be either scalars or fermions. So for the example that we're going to encounter later, we will in particular focus to the example of the scalars. Okay, so these models have a classical invariance of the equation of motion, and the classical invariance consists in some operation. So first of all, you can view the space of this, the space of scalars of this theory as a sort of as a moduli space of aqua, and we have an action on the scalars given by this. I will be very general at the very beginning. So we have an action of these invariance, classical invariance on the scalars, where this action is labeled by an element of a group, which is generically a subgroup of the symplectic 2n R group, or if you like, it's better said, it's a symplectic representation of G. Then we have an action also on the gauge field, on the gauge field strength, and it's dual. G, it's dual, and it can be computed from the Lagrangian by varying the Lagrangian with respect to F, which is given by a matrix S, which is a continuous symplectic rotation, so it's an element of this representation, and it's convenient to present this matrix in a block form, so where we have four n by n blocks, A, B, C, and D. Okay, so if n is equal to 1, this is just a standard cell to R. Okay, and we'll see example of this. Okay, so G is this invariance group, so it's the group under which the equation of motion are invariant. Yeah, it's a continuous group, and we call it Gaillard-Zumino group. Okay, so this is just to set some names. So this will be the Gaillard-Zumino group, and S is its symplectic representation. Okay, so this is the setup. And so these symmetries are classical symmetry in the sense they are symmetry of the equation of motion. They are not symmetry of the full Lagrangian, so they cannot be promoted at a quantum mechanical level. And this is similar to what happens in axiom-Maxwell case. In the axiom-Maxwell case, we also have a classical invariance of the equation of motion, which is the axionic shift. And in fact, we can write a current which does not behave a conservation, does not behave like a conservation equation, so it's not conserved, right? And the non-conservation is given by this term. And this is similar for the more general model that sits in these Gaillard-Zumino Lagrangians. And the non-invariance is a little bit more complicated. It's labeled by an element of the algebra of the symplectic algebra. But just to give you the form here, also in this case, these classical invariance cannot be promoted to a symmetry of the theory because we know that the current is not conserved. But we know from recent, yeah.
Is there a specific Lagrangian for this
No,
model?
for now I'm being very general. So I'm discussing a large class of Lagrangians.
So simply imposing that there is this invariance, you will get this non-conservation equation is independent on the choice of the Lagrangian.
There is a condition which I will tell you once I go into the more details. Okay, so this is just to motivate a bit this story, but there is a condition that the Lagrangian has to satisfy.
Okay.
But it's a fairly general.
Okay, thanks.
Okay, so we know that the axiom Maxwell case, the axionic shift is if we shift the axiom by rational number, we know that there is a well-known by now zero for symmetry that is not invertible and survives as a non-invertible symmetry. And a similar story will hold for these Gaillard-Zumino models. Okay, so one can try to build the symmetries like it was done for the axiom case, but because of the appearance of the dual field strength here, it's better to actually implement another way of constructing the symmetry, which I will tell you in a second. Okay, so but this was just to motivate that also in this case we see a similar structure, and we have the hope that some of these symmetries might survive as invertible symmetries. Okay, even at quantum level. So the answer is affirmative. So I will tell you how to construct this symmetry later. And so we have a new large cluster of non-invertible symmetries that in a context, since we are discussing models that appear in as low energy effective field theories of supergravity theories, they can be at most approximate at low energy. Okay, and these symmetries are labeled by the intersection of this group and the symplectic to the symplectic group, but with the rational entries. So we'll see how this will come out later. But the element of this group will label the non-invertible topological defect. Okay, so as I was mentioning, this model will appear a lot in string theory compactification or in supergravity. And so it's interesting to understand what are the symmetry that can be at most approximate at low energy because of the law that in quantum gravity the symmetries are not present, or can be in the sense that they can be at most approximate at effective field theory regimes. We also know in some specific models the explicit UV completion in terms of worksheet description. For instance, take compactification of string theory on tori. So we know that the CFT on the worksheet in this case contains well-known topological line defects and interfaces. So then a natural question, a motivating question arises, and it's, do these defects on the worksheet have anything to do with these new symmetries that we constructed, these Gaillard-Zumino symmetries? And the other question is whether the selection rules of the topological line defects in the UV completion, so in the string theory completion of the CFT part of the string theory completion, give a sort of quantitative way of establishing which is the scale at which these Gaillard-Zumino become approximate. Okay, so the effective in the effective field theory at low energy. Okay, so we'll come back to this motivation at the very end, the conclusion. Now we'll discuss how we construct these symmetries. So here is the outline of the talk. So I just present you what are these Gaillard-Zumino models in very general. So I will give you a bit more details in a second, and why they are interesting, especially from an high energy point of view. I will then tell you how to construct these Gaillard-Zumino non-invertible topological defects. So what is the procedure that we implement to construct them? And then I will focus on 3 examples, a warm-up example, which is well known, we know how to construct a symmetry here, but I will review this in our framework. And then I will discuss tau Maxwell example, so an axio-dilaton coupled to Maxwell theory, so this is a typo, and a bosonic set, and then a final model, which is a bit more complicated, and it's just a bosonic sector of n equals to supergravity, which is related to Calabi-Yau compactifications in 4 dimensions. Okay, so this is the outline of my talk, and I will start with the construction of these topological defects. Okay, so before going to the construction, let me give you a little bit more details on these Lagrangian. So there is a condition that this Lagrangian have to satisfy, and the condition is that if we is called we call it Gaillard-Zumino condition, and in particular, if we perform a transformation of the scalar or the neutral sector. So we will consider only the scalar case. So if suppose we perform a transformation of the scalar, then the Lagrangian will change in this way, where LS is another Lagrangian, but now that depends on the scalar field and not on the transformed scalar field, and is not invariant and changes in a particular way. And in particular, the condition that this LS has to satisfy is this one. Okay, so this it's the condition, or it's how the Lagrangian changes when we do this scalar transformation. Okay, so this still the field strength and dual field strength are transformed with this matrix S, and the dual field strength is given by the variation of the Lagrangian in terms of F tilde. Okay, so this condition is satisfied only if S is an element of the an element of this group, which is in a symplectic representation, or in a more specific case, it's just a subgroup of these SP2NR. So it's just a symplectic transformation. Okay, so this condition give us that S has to be a symplectic transformation, and it has to satisfy this condition where omega is just the block diagonal matrices, where these are the identity and minus the identity. Okay, so what is this LS? So just to give some interpretation, this is just a sort of this is just a dual theory, or if you like, it's just a physical equivalent theory, and there is a map from the original theory to this dual theory, or to the observable of this original theory to this dual theory. So it's basically this transformation of the scalar becomes a sort of duality transformation on that changes it changes the Lagrangian, changes the parameter of the Lagrangians, but gives a physical equivalent. So it's a dual theory. Okay, so please interrupt me if you have any questions. So this is the setup, and now I will start tell you how to construct these Gaillard-Zumino symmetries.
Sorry, there is one point that I missed. Is there a
Yeah.
specific form of this LS, or this additional Lagrangian that you get when you do this transformation?
This Lagrangian, it's for now it's very general. It just has to satisfy this condition.
I just satisfy this condition.
Yeah.
So this is
This
something
is
that
the only
you want to impose.
Yeah, and
Okay.
also these together with the fact that this has to be a symplectic representation of the group G. So
Mhm.
S is a symplectic transformation.
Okay.
Okay, so the Gaillard-Zumino condition that I showed you in the previous slide tells you another thing. It tells us that the transformation on the neutral sector, or if you like, the scalars, can be reabsorbed by a symplectic transformation of the field strength. So schematically, so this is basically a reinterpretation of the condition that I showed you before. So schematically, if you have a Lagrangian and you transform both the scalars and the field strength in a way, in the symplectic way, then you get back to the original Lagrangian. Okay. Okay, so this is a schematic equation. So the actual condition, the precise condition is the one that I gave you before. But this give you a sort of understanding, can give us a sort of understanding how to construct this symmetry defect, meaning that we start seeing that we have to combine a transformation on the scalar together with a transformation on the field strength and its dual. Okay, so if we combine these two transformations, first of all, we can consider the integral, the integral group, the integral subgroup, which is a representation of SP2NZ, now in an integral coefficient. So this is what flux quantization will impose. So if we want to quantize the fluxes, and this will give us an honest non-invertible symmetry of the Lagrangian of the theory. But this is not the full story, so I will give you more detail how to construct this, also this invertible case later. But just to present you a little bit the result, so this is not the full story, and we can construct more topological defect. which at the cost that they are non-invertible. And this non-invertible defect will be labeled by the group that has a rational coefficient. So a symplectic representation that now it's with the rational coefficient. So, and the procedure, as I already anticipated by this schematic condition, consists in two steps. The first step is to present a transformation, or if you like, a defect that implement the transformation on the neutral sector, so on the scalar. This will be a non-topological defect, okay, because of the non-conservation of the current. And then we will combine this with an interface that implements a transformation of the field strength and its dual, okay? So this is how we will proceed. So we will construct this topological symmetry defect in two steps. Okay, so let me give you the construction of this topological defect. So the first step is to consider a defect which is not topological and implements the transformation of the scalar. Okay, so this can be for any S in a symplectic representation with coefficient in R. We can define this operator or this or defect more precisely. So if you like, if you put this on a spatial slide, this is just an operator which is gauge invariant. And this operator relates a Lagrangian on the left to a Lagrangian, the transform Lagrangian on the right, where we transform only the scalar, or if you like, this is equivalent by the Gaillard-Zumino condition to the dual Lagrangian. So this LS is not equivalent, is not the same Lagrangian as L. So these are different Lagrangian. And since we are treating this as a theory with the field living on the left and theory with field living on the right, this non-topological defect will give us a gluing condition, and this gluing condition will be just on the scalars. Okay, it will be non-trivial on the scalars. Okay, so this is the first ingredient. The second ingredient is instead an interface. This interface can be constructed. We know how to construct.
Why is it not topological? Is J sub t not closed?
No, it's not closed, right? It's the current is not conserved. It depends on F and G wedge. So this is the something that yeah, this is the non-conservation of the equation in general of the current. So therefore, it's not topological. For a generic element of SP2NR, is not topological. Okay. Okay, so then we combine these, so we construct this interface, and this interface, they exist only for elements that are symplectic representation of the group, but with coefficient in the rational, okay? Or we know how to construct this interface just for this case. Okay, so this interface will relate the Lagrangian on the left to a Lagrangian on the right, and will transform from LS to back to L itself. And the gluing condition that we get from here is that the field strength on the left are related to the field strength on the right with this matrix S. Okay, so this is a matrix, generic symplectic representation of the group GQ. Okay, so we would like to understand now how to construct explicitly this interface. So for now, I've been a bit abstract. So this in general, we relate this Lagrangian on the left to the Lagrangian on the right, but I will now give you the explicit Lagrangian expression for these interfaces. And to do this, we use the usual strategy. We split the element, the S element, which is an element of SP2NQ, according to a choice of generators. And we pick a convenient choice. Of course, this can be, it's not the minimal choice, but we pick a convenient choice that consists in the S duality transformation, this rescaling transformation, and finally, this, if you like, this is actually an axionic shift transformation, okay? So all these elements will generate SP2NQ. So you can consider product, and you can generate this element, the general element S. And moreover, by fusing WA, WC, and W omega, so we can construct the interface for each labeled by each, but omega by A and by C, and then we can fuse them to construct the general interface for S. Okay, so now we will construct this generating interface. So this has been, some of them of course have been already constructed. So the interface, for instance, that implements S-duality, it's a famous S-duality interface. So we will relate, so L omega in this case is just the S-dual Lagrangian of L. Okay, so the interface will relate L omega to L, and in particular, we have a gluing condition dictated by this interface that is given by this action of the element omega. And this is just the S-duality wall, which was studied in the past, and it's given by this Lagrangian expression. Okay, so this is also an invertible interface. So if you fuse W omega with, we'll see this later more precisely, but if we fuse W omega minus 1, this will give the identity. So it's an invertible case. But let's understand the non-invertible interface. So we can construct WA. So WA is the interface that is labeled by, or corresponds to this element of SP to N Q. So A is an invertible matrix with a coefficient in Q. And this interface will have as gluing condition, so we'll relate LA to L. So we'll, from the dual Lagrangian, we'll go back to the original Lagrangian. And the gluing condition is just that FL, it's related to FR with this matrix A. Okay, so this interface is, if you like, the generalization to the gauging interface of a non-anomalous finite subgroup of the electric and magnetic 1,4 symmetries. Okay, so this rescaling is interpreted as gauging or 1,4 symmetry gauging of the gauging of the finest subgroup of the 1,4 symmetries. So we know that the Maxwell, so this gauge, this gauge field, we can have 1,4 symmetry, and if we consider a non-anomalous subgroup and we gauge them, we will have that the gauge field and the dual gauge field will rescale in this way. To construct this interface that implements this gluing condition, we can consider the following matrix factorization. So notice that this matrix factorization, it's not unique. So we call this M and E because this will correspond to basically gauging of a magnetic finite of the finite subgroup of the magnetic 1,4 symmetry, and this finite subgroup of the electric 1,4 symmetry. So if you consider this factorization, then we can construct the interface explicitly, and the interface has this form. And for the n=1 case, so if we have only one gauge field, then this is well known, is just the gauging interface that has been constructed for the Maxwell theory. So this is the generalization to multiple Maxwell fields. Okay.
But
And yeah.
So at the beginning you said, look, if you're restricting to the integer subgroup, you're preserving quantization, and that's great. Here you're not. So why is that not a problem?
This is actually what the non-invertible symmetry will do. Let me come back to this okay. Point in 5 minutes. I promise I'll come back, and then if you have more questions, I can answer. I can try to answer. Okay, so for if instead we consider not the rational subgroup, but just the integer subgroup, then the interface provides a rotation of the gauge field, so there is no rescaling, and so this is just an invertible interface. Okay, there is a third interface, a third generating interface, which is also non-invertible, and this third generating interface will implement an axion shift, a generalized axion shift, because now we have more than one Maxwell field. And so this is how the dual the dual Lagrangian will look like is just a Lagrangian where we add a transformation, a transformation like this. Sorry, a term like this. So the two Lagrangian are equivalent only if this C, sorry, this is the same C, it's an element whose Cij are all are all integers. But it's not generically equivalent if these are rationals. And again, to construct the interface, we can pick a factorization of this C, and a convenient factorization is given by these matrices. These are two integer matrices that they cannot. N has to be invertible, but P doesn't. And in particular, this interface can be presented in this way. So we have, this is a bit more complicated than one before. So we have a term on this interface, which is just relating the gauge field to the left. So if you integrate out B, this will relate the gauge field, the field strength on the left to the field strength on the right. And then we have a topological field theory, which is dressing this interface. So this is basically the topological field theory that is coupling to the field strength. Okay. And B, A, and C are gauge field on the interface. Okay, so this interface will implement this gluing condition. So this is the gluing condition that this interface will do. We shift the dual field strength with the field strength in this way, where Cij are the rational coefficients. And WA and WC are not unique. Okay, so they can be, we can pick different factorization and basically implement the same gluing condition. And so there is a question here that also will appear in conclusion, and whether we can actually define minimal, so a notion of minimality for this interface. And in particular, whether this topological field theory can have a notion of minimality. So here it's a bit slightly more complicated for the one gauge field example. Here we have more gauge field, so the notion of minimality is a bit more complicated to come up with. Okay, and finally a comment, WA and WC can be obtained from half space gauging. Okay, so this interface can be constructed by doing the half space gauging procedure. Okay, so this is just a comment if you are familiar with this procedure. Okay, so this is the two ingredients, and now we combine them together. So the interface exists only for we are able to construct the interface only for the rational part. So we consider only the rational element. And so we can combine the non-topological defect with the interface in this way. And generically, what this will give us is the following. So we have a Lagrangian on the left, a dual Lagrangian in the middle, and then thanks to the interface, we go back to the original Lagrangian. Okay? And on the non-topological interface, we'll have this gluing condition on the scalar, and this is something that we already seen on this non-topological defect. And on the interface, we will have this gluing condition on the field strength and dual field strength. And then we can put these two together, and if we put these two together, we construct a topological defect. Okay, so this is the combination of this non-topological defect with this interface give a topological defect, where the gluing condition is the combination of the two conditions, is a gluing condition on the scalar and a gluing condition on the field strength. So this will dictate how the transformation rules on both on local operators and on extended operators, as we will see later, of these topological defect. Okay, so to recap a little bit, so by combining the two operations, we get topological symmetry defect. So the non-invertible symmetry defect are labeled by the rational element. So this is non-invertible follows from the interface, whereas the integral part are just invertible defect. And these are topological, so because they commute with the stress energy tensor. So the stress energy tensor on the left and on the right is the same, and therefore we can conclude that these are topological, okay? Okay, so these are the topological defects. Let me tell you why are non-invertible. Let me go back to the flux quantization condition. So fusion of the Gaillard-Zumino topological defect can be encoded. It's actually encoded in the fusion of the interface. So, or more precisely, the non-invertible part of the fusion is encoded in the fusion of the interface. So, in particular, for a generic element that is not invertible, we can compute this fusion, and this fusion gives us a condensation defect that is different from the identity operator. So the action of on the local operators is the standard action by linking. So we can consider an S3 linking this doublet F and G, where it's generalized doublet. So this can be Fi and Gi. So this is just a short notation for the vector of all field strength, the dual field strength. And this is the action on the scalar. Okay. But the action on extended line operator is instead non-invertible. And this non-invertibility is in fact due to the presence of the interface decorating the interface which are necessary to construct the topological operators. So if we take a generic line operator, which is a combination of Toft lines and Wilson lines with this Li and an It that are all integral coefficient, and we sweep the defect, the line defect across the topological defect, then what we will see that is a genuine operator will become, a genuine line operator will become non-genuine. So it can happen in two ways. So it can happen like this. Okay, if we have so we have a surface. We have a surface attached to the topological defect, which connects the line defect, and here is just a disk. So this depends on a bit on the surface sigma prime and what on the homology structure of the surface sigma prime. But these are the two situations that can happen. Okay, and in particular, this action is that sends a genuine line to a ungenuine line. It's actually the hallmark of a non-invertible symmetries that maps genuine defect into non-genuine defect. And this is indeed due to the flux quantization. So if we transform, if we act on a line defect with a generic non-invertible transformation, so we get a non-genuine operator on this side because the line operator supported here doesn't have integral coefficient, but has fractional coefficient. And so the only way of making sense of this operator is attach this to a surface operator. So this will become an honest gauge invariant operator on the other side. So this is so the fact that the interface that decorate the topological operator do not respect flux quantization is not is just a feature of this non-invertible symmetry, or more precisely, is just the fact that a non-invertible symmetry operator will project out of the from the line from the spectrum of line operators some of the genuine line operators, or in other words, some of the genuine line operators would become just non-genuine operators on the other side. Okay, so any question about these general non-invertible defects? Okay, so this is very usual in the for non-invertible symmetry defect. So let me just now go to explicit example. So the first example is I want to review just the axion Maxwell case. So we can consider a U1 gauge field coupled to a periodic axion. So this is the Lagrangian. So this is a well-known model that has been studied, and a Gaillard-Zumino, and this model fits into the Gaillard-Zumino framework. So it's a Gaillard-Zumino model with n equals 1, so with one gauge field. Sorry. And S is just a U1, which is embedded into the symplectic 2, R group. Okay, so the group that labels this defect is just U1 in general. So the classical invariance is just 1, and it's embedded in this symplectic group. So the action on the axion is just a shift action. So it's a shift by in general by a real number, but we will focus on the rational part, because only for rational part we can construct the interface. And moreover, FNG transform with SC in this way. So this is an element of SP2R, and it's also an element.
Question.
Yeah.
Is P over N in lowest terms?
Is P over N, sorry?
Are P and N relatively prime?
No, they are not. They don't have to be. Oh, sorry. For this case, they have to be. Sorry, later I will relax this condition. For this case, since I consider this as a U1, and I consider a periodic axion, in this case, P and N are coprime. Thank you. Yeah, this is important. But later I will, for the next example, I will relax this condition. Okay, so the dual Lagrangian, it's the one we already presented. This one constructed the defect is just this the Lagrangian with the axionic shift. Okay, so we have this term. So it's not equivalent with C is in Q mod Z. And the topological non-invertible zero for symmetry of this theory have been already constructed. Okay, so you can construct directly from the current by dressing the current operator with a with a fractional quantum Hall state to make a gauge invariant topological operator. Or we present this is equivalent construction, but it's slightly different. So and it fits into this Gaillard-Zumino topological defect construction. And so we like to combine these non-topological defect that implements the transformation of the scalar. So this is the axion current. Okay, so this is the axion current. And this will transform the Lagrangian to the dual Lagrangian, which is this one, with this gluing condition. So the gluing condition of this defect is just acting on the scalar. And then we will have an interface, which you can construct like this, again, specializing the general case to n equals 1. So this is a minimal TQFT coupled to FR. And then we have a term that relates FR and FL just by integrating out B. Okay, so this will generate a transformation that give us back to the original Lagrangian. But what we have is by combining these two operations, a topological symmetry defect, which from the original Lagrangian goes back to the same Lagrangian, but with a non-trivial gluing condition that give us the transformation of the field. So there is a transformation of the dual field strength, GR, and there is a transformation of the scalar field. Okay. And the non-invertible symmetry group here is labeled by this Q mod Z, okay, as we already know from previous works. So this was just to warm-up example, just to highlight the fact that also axial Maxwell fits into these Gaillard-Zumino models. Let me just give you a generalization of this example, which consists in axion dilaton Maxwell. So tau Maxwell is again an n equals 1 model. So we have only one gauge field. And instead of a dynamical axion, we have also a dynamical dilaton, which combine into a complex field in this way. Okay, so as the Gaillard-Zumino model, the classical invariance here is the full SL2R. And the action on tau is the standard modular action on the parameter. Here I choose a bit the inverse, but it's a slight choice, a different choice from the standard one. But this is how the tau parameter transforms. And moreover, we have also a transformation of the field and the dual field strength, which is given by the standard SL2R matrix. Sorry. Okay, so now we have to combine, we have to construct the non-topological defect, and we have to construct the interfaces for a generic element in S. So we can focus on the rational part because we are able to construct only interface only for the rational part. And it is, again, convenient to pick up a set of generators where a set of generators that we have here is given by SA, where SA now is M over E and E over M in the diagonal entries. So these E and M are all integers. And then we have the omega, the omega element and the generic axion shift element. So here I'm not assuming any coprime condition, okay? Okay, so the construction of the symmetry defect is again analogous to the for the element of C, for the C element. So this is the axion shift, is again analogous to the axion Maxwell case. So I'm not repeating it. So it's just the same. It's just that the current this U defect will slightly change its form, but the interface will be the same. So let's focus on the defect labeled by omega and A. Okay, so we want to construct the defect, the omega and the A, and let's focus first on the omega. So the omega is just the transformation on the scalar that sends tau to -1 over tau. So if we have the Lagrangian on the left, on the right, the Lagrangian is just the tau parameter coupled to the dual it's just a Lagrangian with the tau parameter that goes to -1 over the tau parameter. And then we combine this with the S-duality wall interface. And the S-duality wall interface acts on the field strength, the dual field strength, and so sends F into GR and G into -FR. And in particular, gives back the original Lagrangian. So if we combine the two transformation, we get a topological defect. So we go from the original Lagrangian, we go back to the original Lagrangian, but with this non-trivial gluing condition that dictates how this transformation, how this symmetry defect acts both on local operators and on line operators, line defects. Okay. We can construct another generating interface, and this generating interface is the generating interface for the rescaling transformation, or if you like, the gauging of the subgroup of the finite subgroup of the one for symmetry. And so this is the transformation, the non-topological defect that transform the Lagrangian into the dual Lagrangian. And this is the interface which from the dual Lagrangian takes back to the original Lagrangian. And these are the two gluing conditions. So there is a gluing condition that acts on the scalar, just rescale the scalars with this square, E over M square. And this interface instead acts only on the field strength and dual field strength by rescaling in this way. Again, by combining them, we have a defect that takes us from the original Lagrangian back to the original Lagrangian. And in particular, we have this non-trivial gluing condition, which dictates, again, the transformation of the local operators and line defects. Okay, so these were the generating interface. We can compute fusion of this interface. So for instance, we can see that the omega is an invertible interface. So if we compute the fusion of the omega, so this is part of the integral, is a part of the integral subgroup of SL2R. And so this generates an invertible transformation. And in addition, many fusion rules behave group theoretically. Or if you like, the many fusion rules will actually define the defect, the symmetry defect operator labeled by S and S prime. So there is this curly F, it's the same S prime here. Okay, okay, so but DA instead is non-invertible, and its fusion rule is dictated by the fusion rule of the interface. So we can fuse the interface, and from fusing the interface, we get this very general condensation defect. So we have a part that relates the left and right fields, and then we have this topological field theory defined on the defect, which gives us the very general Lagrangian form of the condensation defect. And upon integrating out some of these gauge field and assuming that the GCD of E and M is equal to 1, we can rewrite this condensation defect as a product of the electric and magnetic of the condensation, or if you like, the one gauging of the electric one for symmetry and the magnetic one for symmetry in this way. So where these are, it's a product of two condensation defects, one for the where we condense the generator of the electric one for symmetry, and here is the condensation where we condense the generators of the magnetic one for symmetry. Okay, so these it's very analogous to the Maxwell case. In this case, we have a coupling which is dynamical, but the condensation defect are very similar to the Maxwell with fixed coupling. Okay, so DC also leads to a condensation defect. So if you fuse DC with DC minus 1, we can have a condensation defect, and this was already understood in the past. And finally, the action on the line defect is again simply dictated by the matrix S in SP2Q. And it's a non-invertible action, like the generic case. It maps joining operator into non-joining joining defect into non-joining line defects. Okay, and these action can be read off from the gluing condition. So in particular, from the gluing condition of the field strength. Okay, so to recap, in this model, we have constructed non-invertible topological defect labeled by the SL2Q elements. And we have constructed also invertible topological defects for the that correspond to the group, to the integral group, subgroup of the classical invariant. Okay, so finally, let me go over a much more complicated model. It's not very different. It's a generalization to what to the Tau Maxwell case, but we will see that the Lagrangian actually looks very similar. It's just generalized to many fields, but it's an interesting model because this is basically the bosonic sector that comes from Calabi-Yau compactification of type 2b or type 2a supergravity. Okay, so the models have as n U1 vector field, so it's an effective field theory with n U1 vector field and n minus 1 complex scalar with an axion and a suction. Okay, so I, it's an index that goes from 1 to n minus 1, and then we small I, and big I instead is an index that goes from 1 to n. Okay, so we will have that the kinetic term of the field strength together with the topological term are specified in terms of function scalar fields, and supersymmetry constrains the form of this function. And in particular, this function and the scalar potential K are all determined in terms of a master function which is called prepotential. Okay, but these are determined in terms of supersymmetry, so they are fixed function of phi. And supersymmetry also constrains the form of the scalar potential, so it's not a very general potential, so it has to have a particular form. And its form is such that the Gaillard-Zumino invariance so the classical invariance, so the transformation on the scalar, is simply an axionic shift. Okay, so this implies that the classical invariance is just R to the n minus 1. The action on the gauge sector is just a bit more complicated because it's induced. Well, it's not just more complicated. It fits into the Gaillard-Zumino setup, so we know the matrix that acts on the field strength, but it's the scalar field induce a transformation of this type. Okay, so notice that this transformation is not much different from Tau Maxwell, right? Also here, it's just a sort of generalization to many fields, but we can recognize a sort of modular transformation of this function n ij. Okay, by the way, I forgot to mention that this nij is related to this function n and k is just the derivative with respect to the fields. Okay, to the field phi. Okay, so the transformation of the fifth strand, and the dual fifth strand is given by this matrix S. Okay, so this is just a symplectic representation of this group Rn to the -1, and the transformation in the independent parameter are just these alphas. Okay, so this is why this is just R n -1, even though as on F and G acts as in a symplectic way. Okay, so the form of this matrix is not the most general. So we can determine the form of this matrix for this model. So A has to have this form. D is related to A. B is equal to 0, and C is just much more complicated. But again, it depends on some integral quantities, which are this tensor K I J K and these two other tensor Y I J K and Y0K, and these are all integer data of the prepotential. Okay, so these are all determined by supersymmetry. So in order to have a sensible interface, we have to restrict to the rational part of this group, so basically to Q. So these are the parameters are now in Q. And we will assume here that Q and P are have GCD equal to 1, so they are coprime. Okay. So again, we can use the general procedure. We can combine the construction of the non-topological operator that implements the action on the scalar, and together with the interface. But in order to construct this interface, we need to find a factorization of this transformation S. So this transformation S is very general, and we want to find a factorization in terms of C and A. So in terms of the generators, so that we can construct explicitly the interface and combine them, because we know we have constructed them in general, and so we can just combine them. So we can construct these two interfaces. So we can find this factorization, and we construct these two interfaces. And then by combining these two interfaces, we get the general interface associated to S. Okay, so these two generating interfaces they are just follow from the general Gaillard-Zumino discussion. So this is a rescaling or gauging interface. Again, we have to find a factorization. So this is basically the electric gauging, and this will be related to the magnetic gauging, where electric gauging, magnetic gauging, I mean finite subgroup of the 1-4 symmetries. But with the difficulty here that we have more gauge field, so these are just matrices. And moreover, we have these C interface, which are axionic shifts. Okay, so this again, it's K is given in terms of these N and C tilde matrix. It just fits the general construction. It looks a bit more. It looks a bit complicated, but these are the topological theory that rests these interfaces. Okay, but now we can combine these two to define these non-invertible symmetry defect, and these non-invertible symmetry defect are the combination of these non-topological operators together with the W interface. Okay, so we constructed also this interface for these n equals to supergravity models, and so we find a lot of these symmetries, which in this case are abelian, but nevertheless they are because they are the Rn to the -1 subgroup, the Qn to the -1 subgroup of SL2 and Q, but nevertheless they are non-invertible, and they are new in the sense that they were not studied before. Okay, so let me conclude. So in the last example, so let me just connect to the last example, and then I will draw a more general conclusion. So in the last example, we constructed topological symmetry defect, which are labeled by Q and P, these two integers. And these are, so Q and P are a vector of Qi and Pi. So these are why the group are actually labeled by Qn -1. But in this case, we have not considered the axion as periodic yet. Okay, so it remains a question: what happens if we want to compactify this non-compact group? Okay, and in particular, to compactify, we have to do an identification, or we have to gauge the non-invertible part, which is given by the Zn-1 group. And this the invertible part. And this invertible part is generated by this defect. Okay, so this is the defect that generates the invertible part of this symmetry. So where m are element, so this is dn minus 1. So missing n minus 1 here. Okay, so in order to gauge, we believe that this defect, so there is a bit of a problem here, is that this defect doesn't really commute with dq minus p. So it seems that to construct gauge invariant defect, if we want to gauge these, we have to think about this better. Or actually, what we think is that the presentation of the defect or the interface that rests this defect is not actually the minimal TQFT that can address this defect. Okay, so there is a question here whether we can construct this minimal interface, and we believe that once we find this minimal interface, the commutativity will follow. Okay, but this is again questions that we haven't answered in this paper, but we'll have in mind. Okay, so we built non-invertible topological defect in general in these general Gaillard-Zumino models. So these models have a field content which are a multitude of gauge fields coupled to a neutral sector, which are, for instance, scalars. We haven't done example of fermions. This also will be an interesting case to understand. And these symmetry defects are labeled by this G in a group with rational coefficient, where G is the classical invariance of the Gaillard-Zumino model. And we discuss some explicit example. So axiom Maxwell, tau Maxwell, and n equals to supergravity, the bosonic sector. So the question is, there is a question here to study a Toft anomaly, which can be either pure Toft anomaly or mixed gravitational anomaly. So for the invertible part of the symmetry, one can just inherit the result of this work to assess what are the anomalies of these group of the invertible part. And it would be interesting to study the anomalies, the Toft anomalies for the non-invertible part. Okay, so this is in general, but also for this model. Okay, and this relates to another question that we know that in string theory compactification, the modular space has discrete identifications. So then we can ask what happens when we gauge the discrete invertible part. So usually the modular space in string theory compactification has this invertible part quotiented, so it's gauged. And so we can discuss and we can try to understand what this implies, and in particular, what the anomalies of this invertible part, how they cancel, whether there is a cancellation mechanism in order to allow for the gauging of this invertible subgroup. Finally, let me just conclude with a final interesting set of examples that can be studied. So this is a toroidal compactification of string theory. The effective theory of toroidal compactification of the string theory fits this form. So we have a scalars, a kinetic term for the scalar, which are M is just a matrix. So this is just a trace of this matrix M. It depends on the scalar field, and also coupled to the kinetic term in this way. So the non-invertible symmetry, in this case, also fits the Gaillard-Zumino construction, and they're labeled by ODD element with a rational coefficient. So we have an ODD non-invertible symmetry also in 4 dimension in this case. And we also know the string theory UV completion of this, which is string theory on the toroidal compactification. And we also know that the rational 2D CFT on the worksheet for this toroidal compactification have ODD non-invertible topological interface, which become topological defect at fixed coupling. Okay, so then we can ask the following question: whether there is a way of, since we know the UV completion, whether this provides a laboratory to quantify what is the scale at which the Gaillard-Zumino non-invertible symmetry becomes approximate. And in particular, we can see whether either the string worksheet selection rules or amplitudes with the insertion of topological defect can explicitly provide these scales, or and extend, and this final question would be to extend this to Calabi-Yau compactification, where we also know the worksheet description. And so this it's another set of models that fits, effective models that fits our construction, and has also the advantage of knowing the worksheet UV completion, and so we can sort of understand how these by studying these in more detail, we can sort of understand how the non-invertible Gaillard-Zumino symmetry becomes approximate. So with this, I thank you for the attention.
Okay, thanks very much. It was a nice talk. Are there questions? I only had some questions, but so you basically looked at just scalars, right? Fabio was scalars.
Yeah.
But I guess this is not these models you could write down for more general fields.
Yeah, for fermions indeed.
Yes.
Yeah, we haven't understood any. We haven't analyzed any examples, but yeah, it's so the problem with fermions is that they can introduce chiral anomalies.
Yes.
So it can mix up with other ingredients. The construction of this non-invertible defect can mix up with other ingredients there.
Mm-hmm.
So there's an extra complication.
Yes.
But these are a set of models that is interesting to study.
Mm-hmm. Cool. Daniel?
Yeah, so that last example you mentioned, so if I remember right from the worldsheet picture there, that there's some semigroup structure of these defects, and it comes from sort of gluing current algebras, so all the modes, right? So but you're not sensitive to everything here. You're just sensitive to like the zero modes or whatever. So does this defect actually know more than supergravity would first say? That's sort of the question. Do you know more string theory hidden?
Yeah. So that yes, these yeah. So in this paper, I have in mind this paper, but I'm sure so there are for sure other works on this. So in this paper, they construct the interfaces for this group, and right. So
But
I don't have an answer to this question. So this is something that we are looking at, how this topological interface actually can tell us something about the scale at which these the symmetry that are symmetries only for the effective field theories that I discussed become approximate. So the scale at which these symmetries stop to be symmetry in a sense. Okay. So yeah, sorry, I don't have the answer for this question, but it's an interesting direction that we are looking at.
And in a related direction, I suppose one might consider fusing these sorts of things in turn with some S-duality rule to generate some rational U-duality type structure.
Yeah, that's true. Yeah. It's even more generalized. It's more generalizable, I would say, yes, to other models. I agree. Yeah, this was one of the original motivation, but we sort of got lost in the construction, and now we're starting to go a bit beyond the construction, let's say.
Thanks.
Okay, any other questions?
Yeah, can I also ask something about the original motivation? So at the beginning, you mentioned the string theory worksheet, and you said that sometimes you have this worksheet string theory where you see that there are certain topological defects, and you were asking whether there is a relation with this non-invertible symmetries in the bulk. Can you comment about this? Do you know some example in which you have some explicit relation?
So so again, this is so the answer will be very similar. I don't know the answer to this question, but so what we observe, so what we can and it's so what we observe that these rational, so this transformation on the worksheet implements the same transformation of the non-invertible Gaillard-Zumino symmetries. Okay, so this topological interface it's a combination of an action on the radii of the torus together with a rescaling of the in that case it's a rescaling on the suppose we take O1, okay, so this is an example where I can say something. So suppose we have O1, so this is just a compact boson, and the action of this interface changes the radius of this topological interface, changes the radius, but also combines it with a rescaling of the winding and momentum modes. Okay, so there is a clear dictionary between the worksheet fields or the worksheet operators and the effective what you get in the effective field theory. Okay, so we know the effective field theory dictionary, so how to get from the UV to the effective regime. And the action that this interface implements is very similar to the action of these Gaillard-Zumino defects. Actually, it's the same. Okay, so provided you map the fields provided you map the operators from the worksheet to the target or the effective the action on the effective of the fields, the action is really the same ODD action. Okay, so these suggested us that there might be a connection between interfaces or even the topological defects at fixed coupling and their selection rules, or some amplitudes or some stringly amplitudes computed with the interface with a similar computation in the effective field theory. And so this might then give us the scale at which this symmetry become approximate. But again, this is not a very precise answer. So again, it's work in progress. But it's a very interesting direction in my opinion. So
one of the reasons I was asking is that you said that these non-invertible symmetries are broken then when you couple theory to gravity, while in general
I try to avoid the broken.
Okay.
That same broken, but yeah, they become approximate at a low energy.
Well, but some approximate symmetry at low energy in the UV completion can either be broken or gauged.
Yeah, but the UV completion here, which is string theory, is a string theory in a fixed background. So it's not really the full quantum gravity. So then you have to do an integration over the full background or even the target space, and that can. But we believe that the breaking of the approximate symmetry happens before this.
Right.
So it's not by summing over the full background. So this happens at a scale which is before reaching the UV completion.
But don't you expect that in general, symmetries of the worksheet should correspond to gauge symmetries in the target space?
Not non-invertible symmetry.
Not for non-invertible, okay.
Because on invertible symmetry, they have these selection rules, which depends on the genus. So it changes. It changes with the genus.
Yes, I agree.
And so you cannot gauge that.
I see. Yeah. Thank you.
Okay, Daniel, do you still have a question? You're still unmuted, but I assume you're done.
Oh, I have many questions, but
okay.
No. I
All right. Cool. Let's stop the recording. Let's thank Fabio.